Okay, last video for this bunch. So we so far we have looked at hypothetical data. So when you have a distribution for the future, you say for the future we expect a 10% return with probability 16%, a 25% return with probability 20%, so on. Each of your potential future return has a different probability of occurring. Now, what if you look at historical data? So if you look at historical data, so you take a sample of historical returns. You cannot take the full history of historical return from the very beginning of stock trading because you do not have access to all the information, or your data set would be too big. Or you may have daily returns, monthly returns, annual returns, but maybe the full set of total returns is the return minute by minute, which is impossible to collect. So you collect a sample, a fraction of the full population of historical return, and you have to work with this sample, okay, which is a fraction of the entire population. So you take historical return, so you have n returns, so your average historical return is the sum of all your collected returns divided by n. So the weight, the proportion of each observation in your calculation is equal. So all observations have the same weight, 1 over n. So 1 over the size of the sample. The standard deviation of the sample is the sum of all the observation minus the average of the sample to the power 2, just like exactly what we did when we calculated the variance, but now divided by n minus 1 instead of n. So when computing the theoretical variance, the variance for future potential returns, so we calculated the difference between each potential return and the mean and the expected return to the power 2, but then every observation weighted by its probability of occurring. Now here every observation is not weighted by 1 over n, it's weighted by 1 over n minus 1. Why? Because this gives us a non-biased estimator of the exact variance of the population. Okay, and why is it? So here's the demonstration. You do not have to remember this demonstration. It's only for the pleasure of your eyes. So whenever I use the operator expectation, I put capital letters inside to express the fact that the variable is a random variable. Okay. So if I compute the expected value of s squared, then I develop s squared. Okay, and then I separate all. We separate all the components of s squared. Okay, and eventually, when we simplify everything, we end up having an expected value of s squared, which is equal to the true population variance. Okay, we don't know the true population variance, but if we were able to compute it, it would be equal to the expected value of s squared when s squared is calculated by dividing by n minus 1 instead of n. Okay, but I mean, you may want to look at that. Maybe later on in your studies you will need it for something. It's here. Okay, good for you. Now, we have a population of capital N returns, which we represent by the letter A. So return 1, return 2, return 3, and so on to capital N. So N could be a huge number. So the return minute by minute of the stock market since 1885. Okay, so that's a huge data set. So this population A has a unique average return. Okay, it's not like it has only one, which we calculate this way. So the sum of all the returns divided by the number of observations in the full population, and we call it R0. Okay. Each time we pick an element in A, each time we go and look for a minute by minute return in the population A. So its value can be any element in A. Okay, so which means the variable called value of an element randomly picked in the set A is a random variable. Again, we represent this random variable by the capital letter R. By capital R. Each time we pick an element in A, we expect a value. So the expected value of R, so we have A. So the set of all minute by minute return of the stock market in the US since 1885. Each time I pick a number in that set. So the expected value of this number is the sum of all the returns in this population divided by the number of minute by minute stock market return. It's R0. So the expected value of the random variable R is equal to the average value of the items in the entire population A. All good?